So in this video we'll be seeing how to parse the interrupt descriptor table. We will be using the SIDT instruction to store the IDT value. So I have started debugging my VM, and here every CPU contains the IDTR register. You can read the contents using the R@IDTR. So you can specify the register, and this is the value of the register. You can read the contents at the memory address. You can see these is an IDT entry, and this is of 16 bytes. You can even parse this as KIDT entry 64@IDTR. So whatever the contents at this IDTR address, parse them as KIDT entry 64 interrupt descriptor table 64. So you can see this is a single value, and it contains the dispatch address. So the address of the function that is going to be executed once the interrupt has been occurred. And how you are going to fetch this address is you just concatenate all of these: offset high, offset middle, and offset low. So copy this and paste here. And this is the function it is going to execute whenever the interrupt occurs. So the key divide error fault. So basically when you divide a number by 0, then this interrupt is going to be occurred. So you can also see the descriptor privilege level 0 for kernel mode and 3 for user mode, and you can read the contents using the SIDT instruction. That is what we are going to do in this video. So to use assembly, we can use core arch asm macro. So this contains the Rust compiler will put some assembly code for the assembly instructions. So before that, we are going to write a structure that is to hold the register values. So struct IDTR, and I'm going to mention something that is called limit. So the limit of this IDT table in the 64-bit architecture, the size is 80 bytes. So if you do the SIDT instruction, and it will do the 10 bytes. So we can see these 80 bits. You can see the first 2 bytes. So the first 2 bytes, 16 bits, is the limit, and the last 8 bytes are the register value. And in 32-bit mode, we have the first 16 and 16 bits as the limit, and the next 32 bits as the address. So we have the 2 byte in 64-bit mode, we have 2 bytes and the 8 bytes. So totally 10 bytes. So we can say limit u16 comma register value u64, and we need to represent this one as the C structure. And also one important thing is we need to represent this as a packed. I did not put this one packed representation where attribute value, and I have got lost so many hours because of this. So what this does is it will pack exactly as these size of these bytes. So if you remove this packed, this limit will also be extended into the 8 bytes because of the padding. the padding junk bytes will be added to this limit, and this 2 byte value will be extended to the 8 byte value. So we are going to use packed so that this limit will be only 2 bytes and the register value will be 8 bytes. And also we can say derive of a copy and clone. We can when we want to convert this value as an address, this copy and clone operation can be performed. So we have the structure IDTR. So let's go and do the SIDT instruction. So SIDT, and the next one is out of reg. So this is the inline assembly. Here we need to specify a variable. So let's say this one as AP. So what this macro does is it will take one register, so say RBX, RCX or RAX, and saves that value onto the stack and performs the assembly instruction operation to that register and copy that register value into the variable we have specified and copy back the saved variable saved value of the RAX register. So we'll be seeing in the disassembly how this macro gets expanded into assembly code that uses a register to save the value. So let IDTR is equals to, so let's say IDT is equals to IDTR. We are going to create a structure object. The limit for now is 0 and the register value is also 0. Okay, we need to make this as mutable. Now we need the address of this IDT. Let mute AP is equals to &mute IDT as mute underscore as mute c void. So we are fetching the mutable pointer and converting this as a mutable pointer to the IDTR and finally converting into the raw mutable pointer. So this is what the normal pointer looks like in the C language. Now put this AP. Let's go and try to build this one. Let's see if it's okay. Now we have got the values in the limit and register value. We are also going to use this function is address varied. So this is present in the NTOS kernel binary. So we are going to say link of name is equals to NTOS kernel, and we are going to import some C functions. First one is the debug print. And the second one is the is address varied. So the function takes the virtual address and returns the boolean value 0 or 1 if the virtual address is valid or not. So public function, we can just copy this, and address is star mute c void, that is normal pointer for in Rust, and it returns 0 or 1, so it must be U8. And second function is copy memory. So the first parameter is target address where you want to copy to, and the second one is copy address structure, and this is just a union. It takes whether virtual or physical address. So this is the source address from where the function want to copy, and the third one is number of bytes you want to copy from the source address to the target address. And the flags, we want to specify if the source address we have provided is physical address or virtual address. And the last parameter is the out parameter, so the function returns a value of how many number of bytes it has been copied. So let's go and create this structure. And struct copy address and addr, and we can just copy these attributes, apply to this copy address as well. So if you don't do this copy cron, the structure object will be consumed. So let's go and declare the function signature copy memory. So target address, second one is copy address, third one is size t. So we already imported these definitions from the Windows API C types. So from this Windows API create, so size underscore t, you can check this and use size. So let's call this as number of bytes, usize, and ulong the flags, and ulong I suppose it's u32. Yes, u32. Let's call this as flags u32, and last one is pointer to size t, number of bytes transfer. So I guess that's correct one. Star mute usize. Yes. So I always suggest you use these C type convention here. So here Windows type p void size t, you can get easily confused. So it's just a good way to remember all of these, some basic u32, u8, c void, etc. So now we have declared all of our functions. Now we need to check if the IDT value contains a valid address or not. So if is address varied of IDT dot register value is equals to 1, then only we are going to print out the value. So let's first print out the value. So we are going to use percentage I64 D. So I64 is integer 64 and the format is in decimal format. First I thought we need to use like printf style format specifiers, but it did not work out, so we will be using this one. So IDT dot register value, we can put some information here, IDTR value like this, else we are going to print address is invalid. So make sure you have the null byte at the end, otherwise this will be the next string will also get printed, because these strings will be on the stack. Okay, let's go and try to build this one. So I expected star mute c void. Okay, now we are good to go. So let's continue here. So I have already registered this test driver.cs as a service. So start test driver. Let's also run the debug view. And we can see the value, IDTR value. So this is the IDTR value we have got. So let's see if this is a valid address or not. We have printed this in the decimal format. So FBDB 1000. So we need to switch to the other CPU, because our code can be run by another CPU, and switching to the CPU 1 and 2. So here you can see A680 FBDB 1000. So this is so on the CPU 3, so I have only 4 cores assigned to this VM. So on the last CPU we have our driver got executed. So we have successfully fetched the register value, and now we are going to retrieve the 16 bytes at this IDTR value. So these 16 bytes. So these table contains 256 entries. You can do a loop from the base address onwards and read 16 bytes in each iteration. So before that, we are going to construct this IDT entry 64 structure, so that you can directly reference this as a offset row, offset middle, offset high. Otherwise you want to specifically fetch these bytes, so that's another headache. You can copy this structure and paste here, and IDT entry 64, or we can call this as IDT entry. And the first offset low is U16, so you can see the 2 bytes, so 0 to 2, and the selector is also 2 to 4, 2 bytes. So basically these members are not that useful, but anyway we just use them in our structure. And from 4 to 6, so this is also 2 bytes, so the entire 2 bytes can represent some values according to the position. So you can also get those positions. So you can see the position 0 from 3 bits, you can see this value. From position 3, 5 bits. So from position 8, 5 bits type, and position 13, 2 bits. So if you add all these bits, you will get the 16 bits, which is 2 bytes. 3, 5, 8, 13, 15, 16. So this we can group all of this into single U16 value. So we can say reserved type DPL, so 2 bytes, and offset middle is also 2 bytes. Here you can see from 6 to 8 U16, and so offset high is the 4 bytes. You can see 8 to C, 8 to 12. Offset high is U32, and the last one is reserve. That one also 4 bytes, because C is the 12 and we have the 16 bytes. So you can also specify the size of entry 64. You can see the size is 16 bytes. So obviously from C onwards, this is the last member reserved, and this one is U32. So we are good to go. We have created the structure IDT entry. We need to read the 16 bytes from this IDTR register value. Okay, so copy memory, target address is IDT dot register value as mute c void, and copy structure. So we need to copy is equals to, and the address is the source address we want to, sorry, so this is my bad, so paste this here. So this is the source address IDT dot register value, and the target address is, so we want to store in this IDT entry. Or we can just declare an array, and later we can parse this, cast this array into the structure. So we have declared U8 array of 16 bytes. So so copy all of the contents at the address of A. Number of bytes to copy 16 bytes, and the flags, so the flags, so copy memory virtual value is 2 and the physical value is 1. You can just Google that one. I got link to some GitHub repository. It contains some C code, and they have this definition as 1 and 2, 0x2 virtual, and the bytes transferred. So let's create a variable, and the return value is status success if the entire range has been copied successfully. So I think status success is a 0 value. Yes, it's 0. I think the type should be i32 copy memory. The return value should be i32 because it's similar to the NT status codes. Let result is equals to this one. So if result is equals to 0 and bytes return is equals to 16, then only we are going to print the contents of the array A. So let idt entry is equals to a dot as mute pointer. So now we can print these values. Idt entry dot offset high. Let's go and print that one. Let's print this in hexadecimal. And idt entry dot offset high. So let's call this as my idt entry. Let's build this one. So meanwhile, let's restart the VM. So our VM has been restarted. Now let's build it. So let's also first verify what value is going to be printed. Okay, we do not know what value because there are 4 CPUs. So let's run this first and verify later. So offset high FFF 801. So break the VM. So here you have the values. Okay, we are again printing this in decimal. We did not change the code. Sorry for that. So D88 FB 8000. So this is the IDTR value. So D88 EF, so not this one. So you can see D88 7E FB 8000, and the value we printed for the offset high is FF F801. So DT KIDT entry 64, paste this address and offset high, you can see 801. So we have successfully read the value here. So you can loop over these 256 entries and read all the entry points for these interrupts. Now let's go and debug this our driver entry main function. I'm going to restart the VM again. So our VM has been restarted. Now break into this VM. Now let's put breakpoint at this test driver entry. So this is the function. So you can see the symbol has not been resolved, but the breakpoint has been added. So BR to list the breakpoints. You can see there is one breakpoint. So if there is any driver that is loaded and executed the driver entry function, then we will the breakpoint gets hit. So let's let's continue the VM. So let's run this. So as soon as I hit enter, the driver has been loaded and we hit the breakpoint because the VM has been frozen. And you can see the entry point. You can view the disassembly here. So make sure the RSP is highlighted, so it always points to the top of the stack. So you can see we are making room for our function variables. So hit P and hit P and P, and here is the interesting part. So move word pointer. So word is 2 bytes, right? So here you can see we are setting the 2 byte value limit and register value, that is 8 byte, as 0. So that is what this code is doing. Copy the 0 into the word pointer. So RSP plus 36. DW RSP plus 36. So this is the these 10 bytes is the IDT R register structure. So we have defined this structure here, IDTR. So 2 bytes and the 8 bytes. 2 bytes and 8 bytes. So we are moving the 0 value. So let's P, and the 0 is still 0. And now we are going to move 0 at the register value member. So you can see the offset 36, 38. So these are two offsets. So that means this is obviously the IDTR structure. We are copying the values. So hit P again, and now you can see the RX register contains the address of RSP plus 36 because we have written an assembly macro. So the address of that will be stored on the RIX register, because you don't need to create another variable for AP because you can just directly store this in the RIX register. So load the function, load the address. So this 5A468846 is the RSP plus 36, and this value will be loaded into RIX. So let's P. So you can see okay, 8846. Okay, so the same value has been copied into RX. Now move that value into RSP plus 40, and now do the SIDT instruction on this RIX. So now so this is my our structure. The first 2 bytes are the limit, and the next 8 bytes are the register value. Now if I hit enter, so these are the same values. Now if I hit P, continue, now this structure gets filled by the values. Now if I do this, you can see the FFF is the limit, and the next one is the IDTR register value. So you can confirm this one by again reading the IDTR register. So you can see this is the our current CPU. Since we are disassembling this code, we have automatically switched to that particular CPU. So FFF DB0044474000. So you can see we have successfully read the IDTR register value. Now we are again copying this into that RSP plus 40, and now we are just calling the function is address varied. So you can see is address varied. It will call the is address varied x function, so it will return the value in the AL register, so the lowest of RIX. So we are comparing. If this is equals to 1, then only go to this inside the content. So that is what it is doing here. So you can see the AL value, the last byte is 1. So jump not equal to, so since it is equal to, we are just continuing here. So this instruction gets executed. Next LEA RIX. So I think next we are so from here onwards it's just normal. So it's just declaring an array and calling the copy and debug print. So I just wanted to show you how this assembly macro expands in the assembly. Okay, so that's all for this video. You can try to loop over these 256 IDT entries and copy all of these values.